All right. So we'll kind of take a look here. We'll kind of pick up where we left off. So that problem set is kind of already out there. With that, what session we do at the end of the day on Tuesday. So that's all the old stuff we talked about in terms of interaction terms. Right. So that's just specific to those. After class today, I think we'll have gotten through everything. I'll post the next quiz. So the last couple practice problems here related to kind of some of the data issue stuff we talked about this week. Most of this quiz is going to be interaction terms, right? There'll only be a couple questions over what we talked about this week. We'll kind of use some of what we talked about this week moving forward. But you'll see that quiz pop up after class once I get back to my office, right? I'll have that probably set to be due at the end of the day next Thursday. So a couple more days. You've had these practice problems and think about the interaction term stuff. There's a little bit of new material from this week, so some time to kind of review those questions before you take that quiz, okay? We'll keep using this data issues file. I kind of have this Monte Carlo file I also posted up here. I'll dive into that a little bit. It's a little bit further than what I'm going to expect you to know, but I think it's kind of interesting for us to kind of revisit some of these concepts that we're talking about. So where do we leave off last class? We're thinking about missing data. We're also thinking about, well, what happens if I move this Zoom thing so it goes away? If we've got some measurement error, and explicitly we were talking about it exists in our X or our kind of, independent variable, okay? We said if it's non-classical, it doesn't really matter. So if we kind of think about the difference between classical and non-classical measurement error, classical measurement error meant that the measurement error we're seeing is not related at all to the underlying values of X, right? So this is the idea. If I try to ask people, about what their current income is, they're not maliciously lying. They're not going to overinflate depending on what their actual income is. They're just going to tell you the value of the thing is close. They're going to round up, round down. There's just some kind of random measurement error. It doesn't depend what their income was. They're giving you their best guess, right? Sometimes they're going to be a little bit higher. Sometimes they're going to be a little bit lower. So that covariance of the X variable and the measurement error that we're seeing, probably, to keep this kind of shorter, I put error in here, but we're thinking about measurement error, is going to be 0. So what did classical measurement error do when we were kind of running our regression? So the estimate we saw when we're using the self-reported data that has measurement error, we went back, I went through this line by line, so I'm not going to expect you guys to know this, right? But we kind of showed this was going to be, where is it? There it is. This is going to be our bias, okay? Now, this is only our bias if one of the assumptions we made here was the covariance of X and the measurement error, right, is equal to 0. If that's the case, then the covariance of X with our measurement error, that part went away. And we were just kind of left with this, a little bit of algebra. We could kind of show, rewrite it in this way, right? So even if we have classical measurement error, essentially what that's going to do, it's going to create more error, right? It's random, right? But when we're estimating this coefficient, it's going to multiply it by this fraction, which we said if I have the variance of the X variable over the variance of the X variable plus some additional term, that'll always be less than 1. So it's always going to pull our coefficient closer to 0, or we caused attenuation bias. But one of the key assumptions we made there was that we had classical measurement error. It was completely random. If in fact that measurement error is related to the X value, so let's say this was the idea that people with higher incomes might tend to underreport, whereas people with lower incomes tend to overreport, right? That measurement error in which they're self-reporting their income depends on what their actual income was. Well, now this assumption is violated, right? And so it won't simplify down to this. It would be much more complicated. We won't dive into exactly what it would be, right? But if we have this classical measurement error, we won't just have an attenuation bias. Our bias could be positive, could be negative, depending on the covariance of that measurement error with our X variable. We can't say what's going to happen to our estimate. Okay? And so I'll kind of look through some examples here in a little bit. But basically, if we have classical measurement error, oh, come on. There we go. We get this kind of nice attenuation bias. If it's non-classical, we don't know what the bias is going to be. Okay. So before we kind of jump into Stata to look at this, excuse me, we're also going to think about what if I just have measurement error in my Y variable, right? So let's say I just have some, people are self-reporting, but I'm using my Y variable instead of my independent variable. I'm thinking about it's in my dependent variable. Okay. So if that's the case, right, then I'm not actually observing the actual Y values. I'm observing the actual Y plus this measurement error from this like self-reported data. Okay. Well, if I just add and subtract that measurement error to the same side of this equation, have I changed anything? No. So essentially that measurement error, when it's in my dependent Y variable, all it does, right? So I now kind of write Y that includes the measurement error. It includes some additional error that I'm not capturing using my explanatory or my X variables. So all it does is create more variation here of what I can't explain. Okay. If that's the case, our assumption in these regressions is that the expected value of the error term, given our X values that we've included, is 0. This was the idea. We're coming up with a line of best fit. So okay, so let's see if that fixes it. All right. So when we were looking at this, we said, here's X, here's Y. This was like all of our Y values. Right? And we were trying to come up with a line of best fit such that at any X value, the errors we were making, the expected value was always 0. Right? Now, if our Y variable now includes that measurement error, then at any point, we're going to see some Y values that are higher, some Y values that are lower than what they should be. We're still going to have that same line of best fit. So in both cases, the S. Is that more interesting than what I'm doing? No. So let's say I run this regression, I come up with this line of best fit. I'm still going to get that same line of best fit, but the data is more spread out, right? So I can come up with these same estimates, but what's going to be impacted? So I can find the same size of the coefficient, but my standard errors are going to be larger, right? So what is threatened by measurement error in my dependent variable is going to be our statistical significance, okay? So measurement error in the X variable cause some bias in our estimates. In the dependent variable, it won't necessarily cause a bias in our estimates if it's just completely random measurement error, but it will kind of change our statistical significance. Okay. So that's kind of the idea there, right? And that's because if it's just random measurement error, that condition we had that the error is not dependent on the X value is still holds. Okay. So what can we do here? So I've got kind of dependent measurement error. I drew that out, but we're going to take a look at what this looks like in Stata. I think seeing some work with the actual data, this will all make a little bit more sense. So I'm going to, oh, and this is where I probably forgot to update it from last class because I think this was the wrong, yeah. So let's see, let's open up that life expectancy data. I should probably make sure I update this global path just in case we want to use it again. There we go. So I'll open up that life expectancy data. We looked at some, oh, what did I do wrong here? Deleted both of these on accident. Oh, what's happening? No, something stuck. Hold on. One of my keys is stuck, I think. Okay, let's try this again. All right. Oh, I see. It is this button. There we go. This is an old keyboard. Maybe I'll have to write the people. Okay, there we go. All right. So we looked at some like missing values. I'm just going to replace GDP here and scale it just to make the numbers easier for us to look at. Otherwise, it's going to be like e to the negative, right? A really, small number. And so I'm just going to replace that variable by scaling it. So if I run this regression of GDP on BMI, okay? So I get this estimate of about 60,000, right? That's what it should be, okay? What I'm then going to do is this thought experiment. I'm going to create some completely random measurement error between 1 and -1, just completely random. Okay, so this should be our classical measurement error. It doesn't depend on x at all. So if I create that measurement error, and then I create a new variable, which is BMI, my independent, my x variable, where I include that measurement error. So I'm essentially now working with like this incorrect self-reported data. I mean, it's not self-reported, this is a thought experiment, right? If I now run my regression, where I've not using the actual BMI values, but the BMI values that include measurement error, what should happen if it's completely random? We said that it should be closer to 0. We have attenuation bias. So I can prove this to myself using this data because I've created the random measurement error. It doesn't depend on x. Sure enough, I don't have 60,000 anymore as my estimate. I'm only getting 56,000. So it's going to be pulling it down, right, towards 0. Okay. Now, I don't think I have this. Oh, I do. Good. Sometimes I even surprise myself, right? So let's say now I want to run this regression, and I'm going to create even larger measurement error. So instead of pulling this random number from a uniform distribution of 1 and -1, it's going to be from -10 to 10. So a much wider variance. But if we go back to our slides, and we said, okay, what's that attenuation bias? The larger the variance on our measurement error, what should happen to this fraction? If I'm making the denominator larger, this fraction will be smaller. I then multiply the actual coefficient by a smaller value, it's going to be closer to 0. So if I have more variation in my measurement error, which is what we're now going to have in this second case, because it's not just in between 1 and -1, it's in between -10 and 10. So I'm going to create this new measurement error, calling it measurement error big, add it to my BMI, and that's kind of like my new self-reported data that has an even larger measurement error in it. Okay. So I'm going to run that and now run my regression where I'm using this variable that has a lot of measurement error. It's still random, right? So when I run this, what should happen is that fraction is closer to 0. So it's going to pull my estimate closer and closer to 0. Sure enough, if I run this, I now not only see like, what was it before? 56,000. It's only 9,000. It's really, really close. So if I have this measurement error, if there's a lot of just random variance in it, it can skew my data or skew my results quite a bit, right? I'm not going to be even close to the correct estimate here, right? So the effective BMI of a country going up by 1, we knew using the actual data, it should increase GDP or predict a GDP by 60,000. Here, this would suggest it only increases it by 9,000. We're understating the effect by a lot. Okay. Any questions on that idea? So once again, sometimes it's like theoretical stuff. It's easier to prove it to ourselves using some data. Right? Here we're kind of creating fake measurement error, but that would be like if it actually existed. Now, if we come back up here, so if I look at my non-measurement error variable, what's also happening is I create or I have more measurement error. Well, notice what's happening to the statistical significance when that measurement error gets added in. Well, it looks like it's still 0. But why can I say that my measurement error BMI is actually less statistically significant? What is smaller using the measurement error variable compared to the actual variable? My test statistic, right? So even though it looks like the p-value is still 0, I know that if I have a smaller test statistic, my p-value is actually getting larger. Now, still, out to the third decimal, I can't see any difference, but I know somewhere that would have to be a larger p-value, resulting in kind of this lower test. And then if I have even larger measurement error, well, now I start to be able to actually see I'm also not only getting the size wrong, I'm losing some statistical significance, right? Here I'm up to a p-value of 0.02, so I couldn't even say that this has any effect at the 99% level. Okay. Excuse me. Any questions on this before we keep moving? Okay. So we also talked about what happens if I have non-classical measurement. This is kind of a weird one. I'm going to create some measurement error that I know is correlated with my x values. So for instance, here I've got, I'm going to call it measurement error 2. So here the measurement error is the old one I created. So there was a random component to it. But part of that measurement error, I'm also going to add in 0.1 times the BMI. I'm automatically making there be some correlation between the measurement error and the X value of BMI. I'm artificially doing this. Now, it won't be a direct relationship, right? So it's not like I'm actually including kind of a scale version. It's because it also incorporates just some randomness as well. So there is some randomness in non-classical measurement error, but a component of it will be related to those X values. I'm automatically doing that here because I made the measurement error a function of the X values. This is kind of an extreme case or extreme point. So here, now I'm going to have that countries with higher BMIs, they're likely to have higher measurement errors, right? They're getting this amount added into the measurement error that's dependent on their actual BMI measures. So I'm going to create this new BMI variable that includes this measurement error that is non-classical. Okay. If I then run the regression of GDP, and instead of the actual BMI values, I use these BMI values that incorporate this measurement error that's non-classical, we said, I don't know if it's necessarily going to be closer to 0. It may be, but it could also be higher. Right? So if I run this regression, instead of that, and I can actually run these back to back so we don't have to keep scrolling. So here was like the actual value. Here was the one that had measurement error. So instead of 60,000, I'm seeing 51,000. Now, if you run this on your device, you might not see 51,000. Why? Because we're all creating different random measurement error, right? So you should see a value that's probably close to this, but it might be a little off because everyone's random numbers will be different. So one thing that you could do to make sure you're producing the same values I am, you won't need to know this for like a quiz or a exam or a problem set. But if you use this kind of feature where you set the seed, this is essentially like it's getting you random numbers, but it's starting from the same point so everybody could replicate the values. So instead, let's go kind of up here. We'll set that seed so we're all working with the same values. And then we can kind of come down here, create our measurement error, and you should get the same kind of random numbers I am. Right, so if I reran this code using this seed, right, I should get the same value. So I'll do that. All right, and we'll come down here to where we left off. So we're creating that non-classical measurement error, but part of my code I didn't run earlier, was setting that seed. So if you run the code up to this point now, you should have the exact same random numbers I am. You don't have to do this in any assignment or anything, but this kind of helps as we're moving forward. So I run the regression with no measurement error and then that non-classical measurement error. What do I see? My coefficient is lower. Okay. Now, it doesn't necessarily have to be the case. So if I looked at instead a second case where now my measurement error is still a function, or it's still going to be correlated with BMI, but now I've built it in so that it's a negative covariance, right? It's negatively correlated with BMI. So if I do this, once again, we know that correct value should be 60,000. Now the estimate that I see, if I run all of the code, is now actually higher. Right? So whether or not that bias will be positive or negative depends on what that relationship is between the X variable and the measurement error. But going into like actual data, like instead of creating the measurement error ourselves, we don't know what that's likely going to be. Right? Now I might be able to guess, right? This is my example of maybe I'll be able to guess that people with higher incomes underreport, or I have negative measurement error, or I might be able to guess maybe people with higher incomes don't want IRS to know, so maybe they underreport, right? But I don't actually know that without the data, right? So we don't really know what's going to happen to our estimate in case, in fact, we had two situations here where depending on what the measurement error relationship to X is, depending on what that non-classical measurement error looks like, we could see higher or lower estimates. So this might look like a question on the quiz, which is that if we have non-classical measurement error in that independent X variable, we have no idea what's happening to the bias. If it's classical, we always know it's going to be closer to 0. Okay. Any questions on this idea? before we keep moving here. Okay. I had one here, I could create any kind of measurement error I want. So this one is like, I've got random measurement error, but then instead of like knowing that it's like negative or positive, I just like multiplied it by BMI and then multiplied it by, you could do a similar thought experiment and you're still going to see like changes that coefficient. We just don't know how it's going to change. So that's a problem, right? If we have self-reported data and we don't know what that non-classical measurement error is, we don't know if the bias is going to be positive or negative. Okay. And then I have some other ones here. It doesn't really matter. I mean, I could run this and see, okay, and stop. Now, instead of being lower, now it's like not only lower. If I have non-classical measurement error, it's not just causing it to necessarily be higher. It could switch the sign. Right? Or what did it do to my statistical significance? Not statistically now any different from zero. So if I run this regression with the measurement error, potentially, if it's non-classical, I think there's no effect when there actually is. Okay. So non-classical measurement error impacts our estimate, impacts our statistical significance, but we don't know which direction. Okay. Seeing a couple confused. Any questions here before we keep moving? You're working along with me or running this code. Okay. So create like a little summary for us here. We're kind of writing this down. So if we have classical measurement error in X, the estimate we see is always going to be lower. And when I say lower here, the absolute value, right? It's going to be closer to zero. If it was positive, it'll be closer to, a smaller positive value. If it's negative, it'll be a smaller negative value closer to zero. If I have non-classical measurement error in that independent variable, we don't know what's going to happen to that estimate. Could be higher, could be lower. Now, the other one we kind of talked about is what if I have this classical measurement error in my Y variable, right? So we said if it's classical, this actually shouldn't cause any difference in my estimate in terms of its size. Right? However, it should decrease its statistical significance. So we haven't looked at this yet in Stata, but that's what we're going to do next. Okay. So I have these kind of three different situations for our measurement. So we'll go back and say, okay, we're still running this regression of BMI and GDP, but now let's say the measurement error is not in BMI, it's in GDP. It's in my Y variable. So I'm going to create this random measurement error where I'm just taking GDP and adding in that measurement error we created earlier, which was between 1 and -1. So it's completely random, it's classical. If I do that, now compared to the actual values, that 60,000 that we were finding before, if I use that Y variable of GDP that now includes the random measurement error, what we're going to see is hopefully my estimate hasn't changed at all. Oh, why did it not change at all? Because I have this completely random measurement error. Wait, no, yeah, that's right. Right. So I've got kind of this completely random measurement error. And this one, just because the data set's a little bit larger, it actually looks like it didn't change my test statistic. Right now, it probably did out to the third, fourth kind of decimal. But this kind of goes to show we don't really need to worry as much if there's measurement error in our Y variable. It doesn't change the size of our coefficient. Now, if I had non-classical measurement error in that dependent variable, so now like the measurement error depends on Y. If I do this, now the estimate I see could change, right? Could be way off, right? So the only reason that we have the same coefficient, if they have measurement error in the dependent variable, is if it's completely random. If it's not, it kind of goes back to the other situation. Like if we had measurement error in the X or the independent variable, we don't know what's going to happen to the estimate. Right? So here, kind of the fourth scenario we could add in here is if I have non-classical measurement error in Y, we have no idea what's going to happen to that coefficient. Okay. So basically, the end result, I'm just summarizing this, non-classical measurement error is a really bad thing because we can't even put a sign to that bias. Classical measurement error, if it's in our X variable, it's still bad, but we can at least say it's going to be closer to 0. If it's going to push it closer to 0, is that going to make it more or less likely we think there's an effect? Well, coefficient of 0 would mean there is no effect. So it's almost like if we have classical measurement error in our X variable, it's kind of like we're playing it safe, right? Because what we're always trying to do is find this causal relationship. Is X impacting Y? This is going to make it less likely we actually find a causal relationship, right? It's going to push it towards 0. Now, if it's if it's classical measurement error in the Y variable, we don't really have to worry there if we're getting the correct size at all, right? If it's completely random, we get the exact same value. So classical measurement error, a good thing to make it simple. Non-classical measurement error is a bad thing, no matter what variable it's in. Okay. Any questions on that before we keep moving? Okay. What do I want to do here? So this is us looking at random missing data. Where are we at in time? So we'll keep going here. If I have time, I'll come back to these Monte Carlo simulations. So go skip back or skip ahead. We went through all this. Classical, non-classical. We looked at all of this. Blah, 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 blah. Okay. So we kind of looked at this in Stata. Oh my gosh. There we go. We'll then kind of talk about something else that is a little bit more simplistic. It's just kind of interesting to think about when we're looking at data, some of the issues that can exist. Okay. So there's this age-old example of the 1936 presidential election. So what happened is we know who won the election, right? We know what the actual votes look like. But has anyone starting to get, you guys are young enough, you might not know, have you ever heard of the Literary Digest poll? So my grandparents would have had like a subscription to this thing. It was like this little magazine that came out and it like had current events. It was something like 50 years ago, a lot of people had a subscription to, right? Nobody even knows what it is now, right? But back in 1936, it was like a national kind of publication. They sent out everyone who was kind of registered, they sent out these survey cards. And they were like, we've got this really cool idea. Let's see if we can predict the election before it actually occurs based off of 10 million surveys. That's a huge sample, right? That should be pretty good at predicting the outcome of the election. So they sent out these 10 million surveys. They got 2.5 million back. Still a huge sample, right? They predicted that in a landslide, Alf Landon was going to win the popular vote and the electoral vote. Well, I've never heard of Alf Landon before I read this example, so we know he didn't win, right? So what went wrong, right? So we kind of have two biases that can exist, or biases that exist. One is the selection bias. So let's assume when they sent these 10 million survey cards out, what if they happened to over-select, and I believe Landon was the Republican candidate, they somehow sent 7.5 million to Republicans and 2.5 to Democrats. Even if those two groups responded at the same rate, I now have a sample that is over sampling Republicans compared to, like, we know on average is about a 50-50 split in the United States. So I could have this selection bias if I was accidentally sending more of these mailers to Republican, kind of traditional Republican voters. So the non-response bias would be, all right, I make sure I solve the selection bias. I make sure I'm sending 5 million to register Democrats, 5 million to register Republicans. I then kind of get those back. Well, what if Republicans were more likely to respond to these surveys? I'm then going to have a sample that is overrepresenting Republican voters. So I could have both of these biases exist in my sample. So let's just think about the first one. So the selection bias would be I accidentally sent too many surveys to Republicans. Well, in 1936, the way that this magazine got these names and addresses to send out these random surveys was from telephone books and car registrations. Who owned cars in 1936? People with a lot of money, right? Who had a telephone line? Well, I don't know how much you know about history, but like it wasn't like everyone had a telephone back then. Like you actually had to pay to have a telephone line ran out to wherever you were living, right? And if you were in the city, there's usually lines there. But if you're out in the country or rural communities, you're probably kind of having to pay for your own. So we've got wealthier individuals who are coming from non-inner city areas. Higher incomes tend to be correlated with Republican voters, right? And living out of the city tends to be correlated with being more likely to be Republican. So this process in which they used to get the names, they were likely causing a selection bias. They were sending more of these mailers out to Republican voters as opposed to Democratic voters. So there was some researchers who went back out, found all these names, and then like sent out another survey to say like, okay, who did, or sorry, they had the same names before. They also just sent out random surveys to people who voted in the 1936 election. They made sure they didn't just use car registration and telephones, so they were trying to get a more accurate kind of sample there. So what they found was in 1936, if you did own a car and a telephone, you were more likely to vote for Landon. If the entire election was just based off that, Landon would have been one of our presidents, right? The problem is when they went back and looked at people who only owned a car, so these were like wealthier individuals, but they lived in the city. They didn't have, or sorry, they were wealthy individuals who didn't live in the city because they didn't have a telephone line. 59 or 60% actually voted for Landon. And if you didn't own a car, but you only had a telephone, probably poor individuals living in large cities, 62% of them voted for not Landon, but Roosevelt. So we were only seeing people in the sample from this category. We were missing all these people, right? And in fact, if you didn't have a telephone or a car, right, you were not wealthy and you lived in the city, or sorry, you were not wealthy, you didn't live in the city, 72% of them voted for Roosevelt instead of Landon. So, you know, the final kind of results of this election, 57%, look a lot closer to if we would have had everybody in our sample. But the way they sent out these surveys, we only had this group. Okay? So this is kind of a nice example where we can start to think about selection bias. And we're thinking about data, especially when it's survey-based. Who is more likely to send me back a survey? So I think about this as like, I get these all the time. And I'm like, my time is valuable. I'm not responding to just some random survey about a product. My grandma will probably, she doesn't, she's got all the time in the world. She's a lot more likely to kind of come, oh, that's interesting. I'll give them my feedback, right? So it's likely you're going to be oversampling sometimes with surveys, like people of a different age, right? Maybe the people that respond are people who only care about that issue, which is then going to be correlated with the actual responses you see. So selection bias is going to cause us to potentially make incorrect decisions or incorrect estimates. And this is just kind of a nice example here. The non-response bias is kind of interesting. I have no idea. I mean, I could come up with a story here. But no matter, let's say they solved the selection bias issue and they sent survey cards out to anyone. Didn't matter if you owned a car or a telephone. Well, no matter what group you belong to, they found that when they sent these additional surveys out, the response rate they got, it was always that people who did actually vote for Landon were always more likely to respond to then other surveys as well. So you can't really solve this. You can't really solve that response bias or the non-response bias. And this is a good example of why. It doesn't matter who I would have sent these survey cards, what category, I'm always just, for whatever reason, getting more responses from the people who actually ended up voting for the Republican candidate. Okay. And I don't know, like you said, you could come up with a story here, but this just happened to be what it was. So we not only had a non-response bias that kind of made us think that Landon was going to win, we also had that selection bias, which is why they got it so wrong. Okay? So we can kind of think about what is some selection bias that's going to exist. Well, it's when we're just missing data. Okay? We're not getting the full data set in our sample. So we'll think about we had completely random missing data. What's that going to do to our estimate? So let's say I had an X and a Y variable, or and I was trying to come up with a line of best fit. So here's all the data points. If I had all the population data, I run my regression. Here's my predicted Y values. Here's the estimate I find. If I'm just missing random data, then the data set I actually have would look something like this, right? I have fewer observations, but if it's random, I'm still going to be having observations that come from similar points in terms of kind of these X and Y values. So what random missing data does, it wouldn't change my line of best fit. So we can kind of call this random missing. Doesn't change that coefficient I'm going to see. But if I have missing data, what's going to be smaller? So something that's going to impact statistical significance. So our test statistic is the estimate that we see, which I said with random missing data won't change, divided by our what? This goes back to like, I don't even know, way back earlier in the semester, our standard error. Well, we said our standard error was going to be kind of this deviation from our predictions, but the part that we really care about was over n-1. Sorry, this is like all in the parentheses, but it doesn't matter. So if I have random missing data, what's going to be smaller? My sample size. Dividing by a smaller value would then increase my standard errors, and then that would cause a decrease in my test statistic. So random missing data, even though it won't change the estimate we see, it's going to decrease statistical significance or decrease my test statistic, increase my p-values, which makes it less likely I'm going to be able to reject. Right? So random missing data just goes back to basically I have a smaller sample size. Right? I'll find the same estimate for beta 1, but my statistical significance is going to be off. Okay. Any questions on this idea before we keep moving? Okay. So that's random missing data. We don't really have to worry about it. It's almost like I just have another random sample that's just smaller. Okay. Now, what if those missing observations are correlated with X? So my estimate there is going to actually now be still be unbiased. So Y. Right? So even if my missing values are correlated with X, I'll try to kind of give you a visualization of Y. It shouldn't matter. And I'll throw a caveat onto that. Okay. So let's say, once again, if I had all of the data and I plotted it, it would look something like this. I come up with my predicted Y values. Here's my estimate for beta 1. If, let's say, I was trying to run a regression of, I don't know, the effect of income on, what's it? I don't know. Maybe like I'm interested in like its effect on BMI since we were using that earlier. Well, if the missing values tend to come from lower income levels, what would this maybe look like? I don't have any values below this, but I still have all of this data. So if it is in fact a linear relationship, what happens to my line of best fit? It's the exact same. Right? Now, once again, I have a smaller sample size than before. So that's going to decrease my test statistic. I forgot a step here. Increases my p-value and makes it less likely I can reject. So we kind of call this, am I making the correct rejection decision? Or refer to that as consistency. So it's going to be a more inconsistent estimate, but it's unbiased because I'll keep finding the same coefficient. Now that would apply if I had a linear relationship. So when I ask you questions about missing data, I'm only going to think about how that's connected to our linear relationships. So we're not estimating log linear, we're not estimating quadratics, right? It's just in context to my linear kind of regressions. The reason why is because let's think about, even if I had the same kind of scenario, so I would be looking at like, I don't know, income and BMI. let's say instead, the data looks something like this. Okay. Well, if I estimated this as a nonlinear relationship, okay, if I use all of my data points, I could find my coefficient on the linear and squared term, and it might give me this line of best fit. The problem is, let's say I was missing all of these values. The missing values are still correlated with the value of x. So I'm missing all of this. Well, now when I estimate my line of best fit, now it might look something like that. So if I have nonlinear relationships, the fact that the missing data is correlated with that x value would matter. If it's linear, or we're estimating this as a linear relationship, it shouldn't matter if that missing data is correlated with x. Okay. I won't push you this far, but just because we've talked about nonlinear relationships, we can kind of think about how that might change things if you were to kind of move to a course above this. Okay. Does that make sense? Any questions on this idea? And the same thing could apply. Let's say instead my missing data wasn't coming from people of low income, but it was coming from people with high income. I still got that same line of best fit. I just have a smaller sample size. Okay. So let's take a look at this here before we kind of go to, I think I've got some missing data correlated with Y. We'll kind of save that for after we do this. Okay. So if we jump back into that do file, I kind of had this next scenario where we're going to use, and I think here I left something out. So if you have your personal device, we've used this before, but I don't know, if for some reason your memory wiped it, or I'm not sure exactly sometimes how it works from Citrix. We need to install these free data sets, and then I can use that kind of birth weight data. Okay. So if I do that, I'm going to create this random number, and I'm going to generate some random value for every observation, and I'm only going to keep some of them. So this, we don't have to worry about how this exactly is working, but I'm creating some random numbers, and I'm just randomly dropping some of the data that exists in this data set, specifically for family income. So I'm going to go ahead and do that. Now, if I were to run my regression of birth weight, and I'm trying to predict that based off family income. So birth weight is just typically used in health research as a good indicator for the health of the child. Right? So family with a higher income, we would expect that the birth weight is going to be higher. They have access to doctors, better kind of higher quality food. So I run this regression, and I find, sure enough, statistically significant, higher income is increasing the predicted birth weight of these babies. Now I've got a sample size of what? 1,388 here. If I then run that same regression, but I'm only using the observations where I didn't have missing family. I created this like random missing, so I'm only going to be looking at 1,000 instead of those 1,300 observations. Well, if it's completely random, we said the size of our estimate should be, so it's kind of intuitive, it's just completely random. Our estimate will still be the exact same thing. Right? We're just looking at, that was where our line of best fit was still the same. We're just missing some data. So we have a smaller sample size. We're going to lose some statistical significance. So if I run this regression, what do I find? Oh, I've been lying to you. I haven't been, but it looks like I am, right? Because my estimate did change a little bit. Well, that's because I just have one random sample. The thought experiment would actually need to be, if I were to continuously take random samples with random missing values, then on average, I would see the same coefficient. So here, it's close to the same size. And for now, just believe me that it should be the same if I were to take an infinite number of random samples with random missing data. I'll show this to you here in a second, how we could do this in Stata. Now, I'm also, because I have a smaller sample size, I can though see I lost statistical significance, right? That p-value went from 0 to 0.002. So it didn't change by much, but it is increasing, making it less likely I can reject, okay? I could then do a similar thought experiment. I could do random missing data that's correlated, but instead here, I'm going to run this Monte Carlo simulation, okay? So this kind of shows you the power of what we can do with Stata. So just to have a comparison, let's run the actual regression where I had all the data. So I get 0.007, I know should be the true value. I'm now creating this program. If I can scroll correctly, hold on. This keyboard and mouse are giving me fits today. So if I've got here, I've created a program in Stata, so you don't just have to use it to run regressions, calculate means. You can actually create programs that it can run. So like when you type in generate, like gen this variable, it's actually using a pre-programmed instruction to Stata. You can create your own programs, right? So I'm going to create my own program that I'm going to call myreg, right? I'm going to open up that data set, randomly create these values so that I only pull out 1,000 of the 1,300 observations. So I'm creating these like missing data samples that are missing some of the observations, but it's random. What we said the problem is if I only do that one time, I could see a higher or lower estimate. The idea is if I could continuously take, say, one random sample with some missing data, another one with some other random missing data, another one, I then do that like 1,000 different times. Then on average, across all of those random samples, I should see on average the same estimate. So here, I'm going to run this 100 times. I'll show you can change this. It's going to basically then have 100 different data sets with random missing values. I'm then going to calculate, after I run this program, the average coefficient I was seeing. This should then give me that exact same result I was finding from the entire data set, which is 0.0074 approximately. So I'm going to go ahead and do that. Takes a little bit of time to run because it's doing this 100 different times. Eventually, we'll get some output from here. This is a little bit easier if you have it on your actual device and not running it from a cloud. There it goes. So sure enough, what do I, on average, I see across those? About 0.0074. Now, I'm a little bit off because to truly get the same estimate, I would actually need to run an infinite amount of samples to be able to prove this to myself with data. But as I'm talking, I can actually do this again. I'll make it do this 1,000 times, see if I can break the computer. Oh, because I have to clear my programs because I'm redefining it to do this 1,000 times now. There we go. So I'll let this run in the background. Well, if I'm going from 100 to 1,000, I'm getting closer to that infinite amount of samples. I should then see an estimate that's even closer to that 0.0074, right? So if I run this 1,000 different times, it's going to take quite a while, but hopefully we'll see I get the exact same value, okay? So as we're waiting for this, are there any questions over kind of what I'm doing here out of general interest or just like, you know, I wouldn't expect you to create these own programs yourself or run these Monte Carlo things yourself on a problem set. But once again, it's just a good way to prove to ourselves that these theoretical predictions are true. That if the data is completely randomly missing, on average, I'll find the same coefficient. Now, the issue is, on average, I'm also going to find a higher or lower standard error. If my sample sizes are smaller, my standard error is going to be larger, meaning my test statistic will be smaller, p-value higher, less likely I can reject. Okay, so I know that that actual standard error, oh, it's not going to let me show you because it's still running these, was whatever it was before. So if I want to summarize this, I could do a similar thing, like save the standard error values, summarize them, and what I'll see is that they're always going to be on average higher. Okay. So I probably shouldn't have done 1,000 here. I probably should have done something like, I don't know, 500 would already be done. But I think it's worth us just giving this a minute or two to wait. So as we're still waiting, the next thing that I'm going to do is kind of show you what if we had non-random missing values, right? So it's the same setup. We're still trying to predict birth weight and family income. We said if this was a linear relationship and I was just missing the birth weights of people who had low income, it was essentially like I just was missing part of that linear relationship. So I still should come up with the same line of best fit. I was just missing these lower values. Okay. So once again, if I do 1,000 times, now I do get exactly 0.0074, right? So this we can kind of prove to ourselves, like could take an infinite number of samples. Doesn't matter if the missing data is random, I get the same coefficient estimate. Now, let's say I do the same thing. So I reopen that birth weight data. I run the regression of birth weight and family income. We're kind of back to our original scenario. So that coefficient is 0.0074, standard error is 0.0018. If I run this regression and I now like bake into it, I'm not randomly missing values here. I'm randomly missing data from, not randomly, sorry. I'm not randomly missing values here. I am missing data from anyone who makes income less than 30,000. So I'm missing part of that line of best fit or part of that scatter plot. Well, if I run this regression, sure enough, what do I get? Oh, sorry. I get that exact same coefficient. Well, my standard is the same. Why? I probably made a mistake here. Because what is family income? Let's see. Because it's not in thousands, right? So I wasn't dropping anything here. What I meant to do, I forgot, it's not 30,000. 30 would represent 30,000, right? So it didn't actually drop anything there. So we'll kind of redo this. So if it is, okay, well, my coefficient went up here, right? How did that happen? Well, this could be what? That instead of a linear relationship, that relationship between income and birth weight must be, if I don't get the same estimate, we had this kind of drawing before that suggested if those X values influence what data I'm missing, it doesn't matter if it's a linear relationship. But if it was nonlinear, that could give me a different line of best fit. So if I was looking at this data set and I had these missing values of anyone with income lower than 30,000, because I see almost a doubling of that estimate, that probably tells me this relationship is not linear, it's probably nonlinear. Right? So this would only work kind of that non-random missing data if I had a truly linear relationship. Okay. And then you could do a similar thing. We didn't quite get there, but you could say, what if the missing values were dependent on Y? Once again, we don't know what's going to happen to our coefficient there because we don't know what values were missed. Right? So instead, let's take a look at what we could do here. So I had this Monte Carlo simulation. Oh, what do I want here? So I think maybe this is good for us to review. So I'm going to go back. I'm going to open up that life expectancy data, scale my GDP variable, be a little bit more specific here. So I run my original regression. So what I'm then going to do is just create a variable that puts in what that coefficient value was, which was 60,000 about. Right? I'm then going to summarize that. What that should tell me is what the variance on that variable was. So the standard deviation was 2.19. Squaring that would give me about 4.18. I can actually pull the variance from my sum command using this syntax. I'm not going to expect you guys to do that on a data set or problem set, but you could do that here. So I now know the variance of my X variable. Okay. If I wanted to, I could tell you what the size of my coefficient should be, because that random measurement error I created before, so this is kind of connecting to what we did before with the life expectancy data, this variance would be 1, so that fraction should be the variance of the variable divided by the variance of the variable plus the variance of my measurement error. So I should find that my new estimate is 49.7, which if we went back to when we actually ran that regression, what estimate did we find? Here. Oh, this changed from what value because I set the C differently. Well, here we can do this. I'll copy and paste this code real quick. So that's what my estimate should have been. If I do kind of create this, I run my regression of GDP on that B and my measurement error variable. Right. what I should find here. What am I doing? I did not like this. I've got my variance of BMI, got +1. I included this here. What am I looking at incorrectly here? +1. Oh. Well, I've got an error in my code here that's not worth going through the time. So instead of doing this, scratch this. Go back to that Monte Carlo kind of thing. If you wanted to, this is what I wanted, the point I wanted to make, because I might do something like this in the quiz. Okay. If I gave you output from like the sum command where you know the variance of your x variable, if I told you what the variance of the measurement error is, you could always tell me the coefficient that you would see if you ran this with measurement error. So the thought experiment will be something like this here. Just so I make sure, trying to think about things that will help you on the quiz. So let's say you have this estimate from the actual data, and you know that the estimate should be 50,000. Okay. I then tell you, you don't actually have all the data, the actual data, you have some data with measurement error in it. If the variance of that measurement error, you would have to be told is, I don't know, in this case, you could do something like 100. Okay. Well, I could then show you output from Stata from that sum command that would give you like the mean, the variance, the standard deviation, etc., of whatever your x variable was. So if you know that the variance of this x variable, or kind of variance of x here, let's say I told you this was, I don't know, we'll do 5,000. Okay. I'd say, okay, if you were to run this regression where you're trying to predict y from x, but you only have the x values that include that measurement error, what estimate would you find for beta 1 now? Well, we said if this is completely random, it should be that I see the true estimate, which was 50,000. I know that that will get multiplied by the variance on the x variable. Here, I'll write this out in general terms just to make it easier. Variance of x over the variance of x plus the variance of our measurement error. So I know this is 50,000 because I have the actual data. If I was told from the actual kind of data, my variance here is 5,000. And then I was given from another researcher that the measurement error is 100 here, I could actually calculate what estimate I would see if I was using the data that had the measurement error in it. Or if I had the data with the measurement error, but I don't have the actual data, you could find this from your output and then back out what the true estimate actually was. Now that only works if someone else has data where they can report to you the actual kind of variance in x and the actual kind of variance of your measurement error. So in practice, you can't do this, but in these kind of problems I can set up for you, I can give you really any three pieces of this kind of equation, one equation, one unknown. You could always then solve for what you're missing. Okay. So that's kind of, related to that measurement error. This could be a question that I ask you how to do. Okay. I would have to give you either the estimate that comes from the measurement error equation, the estimate that comes from the actual data that didn't have measurement error, the variance of the x variable, the variance of the measurement error. If I give you any three of these things, you could always then solve for the fourth. Just to be a little bit of algebra there. Any questions that what I'm getting at there? Okay. I was trying to make it a little more complicated in that do file. This is what I wanted to make sure that I kind of showed you. So is there anything else I want to show you here that would be interesting based off what we talked about? Let's look at this here. Well, for the sake of where we're at in class, I know that we don't have quite as much material next class. So maybe I'll kind of revisit this just so we get kind of a review of this measurement error topic next week as well. So that kind of quiz is open till the end of the day next Thursday. So on Tuesday's class, we'll maybe do a little bit of review here. So if you want to hold off, you can. You don't have to. Basically, all I'm doing here is the same things that we did in the do file today, but I'm running like Monte Carlo simulations where we're doing this like not just one time, but thousands of times to kind of show you even further evidence that what we were kind of looking at was going to be upheld. The other thing I wanted to do here today is publish this quiz, and we'll have the due date to be today. We'll kind of make sure it's just at the end of class here, not 2 a.m., 2 p.m. I'm going to save this. I don't think I have a, if I do have a, you're opening up, is there a code set on it? Might have been. Let's see if I put one on here. I think I might have left this blank. We'll see if I'm remembering correct. Nope, I did have a code. So yeah, 11.17 was the code for today. Okay. So we'll kind of talk through this here together. So if I'm thinking about question one, you can see the answer here, but just kind of let's think through it. Right? So if I have an unknown bias in the estimate for my slope coefficient, so what situations did we say are good versus bad? It's a good thing, or we can put a sign, or we know what the bias is if we have what type of measurement error? Classical, right? So I'm looking for which one gives me an unknown bias, okay? Well, I know the bias if I have classical measurement error in the independent or X variable. That bias is going to be that it's always too, the estimate I see would always be too small. This was where we had the attenuation bias that exists. If I have classical measurement error in my dependent or Y variable, we said the bias isn't unknown. If that's the case, if I had classical measurement error in my Y variable, the bias would actually be, well, we said it's just like I've created more error, right? In that right-hand side of the equation. If it's completely random, I basically find the exact same estimate. We said it's just going to have more variation or higher standard error. So the size of the bias will be 0. It'll only have impacts on my statistical significance. Okay, so if the question were instead, what would impact the statistical significance, right? Well, there, I know that classical measurement error in my dependent variable will actually cause me to make more incorrect projections, right? It lowers my statistical significance. But here I'm just asking about the bias in the coefficient itself. So classical measurement error, we know what bias it's going to create. 0 if it's in the dependent variable, attenuation or pull it closer to 0 if it's in the independent variable. Now we said with non-classical measurement error, doesn't matter what variable it's in, we don't know which way the bias is going to go, right? It's much more complicated, kind of outside the scope of what I want to cover in this class. The extent to which I want you to know how non-classical measurement error impacts our coefficients is just, we don't know, right? It depends on what the nature of that non-classical measurement error is, whether it's positively or negatively correlated with our X or Y, our independent or dependent variable. And what actually ends up happening, it's not just that covariance, it's the size of that covariance. So that's where it gets a little bit tricky outside the scope. We can't just put a sign to it based off if it's positive or negative. We actually would then need to know like the size relative to the actual effect. So we're not going to dive into that. All I would expect you is to answer something like this, which is that if you have non-classical measurement error, doesn't matter which independent or dependent variable it's in, you're going to cause there to be an unknown bias. So you are creating bias, you just don't know if it's going to be positive or negative. So that's going to be the one that causes an unknown bias. Now, if I have random missing data, if it's completely random, we said, what's that going to do to my coefficient estimate? So it's basically like I have a scatter plot, and I'm just randomly removing a couple of those spots, or a couple of those plotted points. I would still end up with the exact same line of best fit, or the exact same coefficient estimate. But even though I know there won't be a bias with random missing data, what will happen to these standard errors? Well, I have a smaller sample size, inflates my standard errors, reduces my test statistic. This is kind of similar to stuff we talked about prior to the last exam, increases my p-value, less likely I can reject. So that's kind of question one. Question two, I think I had to like create this. So there will be a right or wrong answer when it initially submits. I will go back on and just give everybody credit for answering anything. But basically next week, we're going to have a little bit more time. So we're going to do next week to give you a roadmap of where we're going. Panel data next week, which I think if I upload the slides, it's going to be like 13 slides. So not quite as much material to cover. I'm going to focus more heavily on some additional things that we can do in Stata there to set up a panel data. And not to pick on you, but some things that I've talked with the students about, you can actually use some like by sort commands to kind of do some pretty powerful things with panel data. So most of what we looked up to this point, if we go all the way back, I mentioned this early on in the semester, we've either got like time series or we have cross-sectional data. So panel data is when I have like one individual, but I've got like 50 observations, maybe one from every single week. And I have maybe what their hours studied was every week. Right? So I've got one individual, but I've got multiple points in time. That's panel data. We can do some interesting things there. And it can actually help us solve some of these problems that we talked about, like measurement error or selection or non-response biases. Okay. So I digress from this actual question, right? Which is with the additional time next week, I'll likely kind of dive back into that Monte Carlo file a little bit to look at kind of measurement error or missing values. But if this stuff kind of makes sense and like I'm not going to really push it too far on this data issues, the measurement error and missing data stuff, if you'd want to spend more of time next week going back and reviewing like marginal effects from interaction terms, marginal effects from like our nonlinear relationships with squared or log models, or kind of making model comparisons. So I spent a little bit of time on Monday kind of reviewing that. We're thinking about how can I compare log-log models to linear log, to models with a squared term. We can go back and do a little bit more of that as well. So whichever of these you would kind of find more confusing or want to spend a little more time reviewing next week, kind of go with that answer. And there's no right or wrong answer, right? So before I let you get out of here, to give you a little bit more of a finishing roadmap. So panel data next week with some review. We'll probably, if we get through it pretty quick, I might start on what we call instrumental variables on Thursday's class next week. And then that will be the following week. We'll just look at instrumental variables. That should take us both class periods. We then have that week before finals. That's how close we're getting, right? So next week, panel data, then instrumental variables, then a week of review. So I already know in advance, might have mentioned to you guys, that Tuesday class before finals week, we won't have class. I won't be here, right? And so what I'm going to do instead is record a video that goes through what I'll kind of get posted up here before Tuesday's class. I'll get a practice final exam posted. So it'll be me kind of reviewing some of the questions in that practice exam, just like we would if we had class. Then on that Thursday's class before finals week, there we will still meet. And that's where you can ask specific questions you have over that practice final, over old quiz questions, really anything, right? So that's kind of the rest of the semester in a nutshell. Even though we won't have class that week before finals, my office hours that week will be the same. So it's only impacting that Tuesday, some things that I have some commitments I have to do. So that's kind of where we're moving. One more thing, I know you want to get out of here. It's a beautiful day. You should all be enjoying it. My office hours on Monday, instead of being in the morning, 9:30 to 12:30, I'll post an announcement. They're going to be 12:30 to 3:30. So in the afternoon instead of on a day like today, that would be terrible because you want to be outside in the afternoon. But that is what it's going to be just for next Monday. Okay. Otherwise, kind of make sure you're working on that problem set. Let's do next week. Start reviewing for that quiz that'll pop up once I get back to my office. Enjoy this weather. Have a fun, safe weekend, and I will see you on Tuesday.